this video, we are going to surf the Indian Standard Code IS 456-2000, which is useful for the design of plain and reinforced concrete structures and structural members. Introduction. We will start with introduction. Indian Standard Code of Practice, plain and reinforced concrete. It is used for design and analysis of plain and rod structures. It comprises of 5 sections and 8 annexures, which is invariably important, but for competitive examinations point of view, for those who are preparing GATE examinations, IES, UPSC examinations, or any other service commission examinations, they require 3 sections and 3 annexures, which are mostly important and are asked in objective type and any other questions. So let us start with, before we move on to the section 1 of IS 456, just we will start with a question. Do we provide reinforcements in PCC? PCC is nothing but the plain cement concrete. Plain cement concrete in which we are providing reinforcements or not. If your answer is yes, you are absolutely right. What are the reasons for providing reinforcements? Is there any strength criteria to provide the steel reinforcements in PCC? No. The steel reinforcement is nothing to do with the strength, but to prevent the cracks due to shrinkage. To prevent the cracks due to shrinkage, we are providing minimum reinforcement as per IS 456 for also in PCC. Not only in RCC, we are also providing PCC, the steel reinforcement. The minimum reinforcement has to be provided in PCC purposes. So let's start with the section 1 of IS 456. What the section 1 specifies? Section 1 is a general one, which describes the various symbols used in this code. Section 1 is the general part, which is symbol, which gives the description of various symbols. For example, capital A represents the area, small b represents the breadth of beam, shorter breadth of beam or shorter dimensions of rectangular column. Capital D refers to the overall depth of beam, and so on, like this. EL means earthquake load. Like this, we can refer the section 1 general for the description of symbols. Now let's move on to the section 2. It gives the material, workmanship, inspection and testing. So what are all the materials used in concrete? The 4 main constituents in concrete are cement, the binding material, water, aggregates. Aggregates can be coarse and fine. Coarser aggregates and fine aggregates. So now let's start with cement as a material. IS code specifies some types of cement that can be used for concrete purposes. The types of cement recommended by IS codes are: first one is OPC 33 grade, second one is OPC 43 grade and 53 grade. Next, rapid hardening Portland cement, Portland slag cement, PPC Portland pozzolana cement, which is fly ash based, and another one is calcined clay based, and another one is hydrophobic cement, low heat Portland cement. Low heat Portland cement is widely used or adapted in the construction of dams. And the last one is sulfate resisting Portland cement, because sulfate is a adverse constituent. The cement which can resist the sulfate can be used in adverse environment. So sulfate resisting Portland cement. Now the question for you is, what is the ratio of cement mortar used in OPC? Cement mortar. Here the ratio of cement mortar means how much amount of parts of cement and how much parts of sand to be used in case of OPC. How much parts of cement and how much parts of sand? The answer is 1.3. 1.3 refers 1 part of cement and 3 parts of sand. So 1:3 is the ratio of cement mortar used in OPC. So we have seen about the types of cement that is recommended by IS 456. OPC 33 grade is not nowadays used. It is neglected. OPC 43 grade and OPC 53 are widely used as of now. 43 refers to the strength of the cement, 43 Newton per mm square, strength of that cement. 53 means the same, Newton per mm square or megapascal we can say. Ordinary Portland cement 53 grade Ordinary Portland cement 43 grade are mainly used nowadays. 33 grade is rarely used or neglected. Now next move on to another material, aggregates. So aggregate gives the strength for the concrete. Lightweight aggregates as having lightweight and has also with comparable strength. It will provide the strength to the member, strength to the concrete. And the aggregate should not absorb more than 10% moisture. IS code specifies that coarse aggregates should not absorb more than 10% moisture, and it should be free from excessive sulfate. Sulfate resisting cement we have already seen. So sulfate attack means there will be a change in hydration. There will be an effect in hydration of cement. So that there should not be any sulfate attack to the cement hydration process. In order to avoid those attacks, the coarse aggregate should be free from excessive sulfate, or we can use the sulfate resisting type of cement. Now the size of coarse aggregate is governed by three factors. First one is size of structural member. Size of structural member here refers mainly to the thickness of the member. For example, if you take this slab, the slab has the thickness of about some 150 mm, very lesser compared to the beam. Beam have greater depth. So thickness of member, or we can say broadly as a size of structural member, affects the coarse aggregate size. And next one is distance between two main bars. So if you select the coarse aggregate size as some 20 mm, the distance between two main bars should be greater than 20 mm, obviously. So distance between two main bars affects the size of coarse aggregate. Next one is the minimum cover we are providing, that is a nominal cover. For example, if you provide footing cover of 50 mm, that 50 mm has an effect of size of the coarse aggregate, what size of coarse aggregate we are using. So minimum cover, size of structural member, distance between two main bars will affect the size of coarse aggregates. And 20 mm nominal aggregate size are used in general. 20 mm nominal aggregate size is used in general. In general practices, we use only 20 mm nominal size aggregate. For massive concreting, such as in dams, we can use more than 40 mm size aggregates. It can be used. For extremely thin slabs, we can use 10 mm aggregate. It is very lowest value we can use for extremely thin slabs in case. So now the question is, will the shape of aggregate affect the maximum strength of concrete or not? What are the shape of aggregates? We can have rounded aggregates, we can have cubical, angular, we can have flaky or elongated aggregates. So much of shapes are there, irregular type shapes are there. So that shape will affect the maximum strength of concrete or not is the question right now. It will affect or not? If your answer is yes, you are absolutely correct. And which shape of aggregate will give the maximum strength is the another question. So the cubical aggregate gives the maximum strength compared to rounded or any other flaky, elongated, or so and so. Why cubical aggregate gives the maximum strength is the another question. So it has the interlocking property. Being cubical and or angular, we can say it has some interlocking between the aggregates. So the strength will be maximum for the concrete. If you use the rounded aggregate, the void ratio or the voids present in the aggregates as a mass will be minimum, but there will be no interlocking in case of rounded aggregates. So due to this reason, cubical aggregate gives the maximum strength. So far we have covered cement and aggregates, and then we move on to water and admixtures and other materials. Now coming to water. So water should have pH not less than 6. Why? What is the criteria for not being less than 6? Because the water we are using should not be acidic. If you use the acidic water or acidic liquid, we can say yes, acidic water, there exists some corrosive properties. So pH shall not be less than 6 as specified by IS code, and the water we are using should be free from oils, acid, alkalis, salts, sugar, etc., or any other impurities. Seawater is not at all recommended because seawater contains chloride, so chloride will induce the corrosion, so it is not at all recommended. Water is obviously used for mixing and giving. So now next is the admixtures. Admixtures are additional constituents which may or may not be used in a concrete. A concrete must consist of water, coarse aggregate, fine aggregate, and the binding material called cement. Admixture may or may not be used, depends upon the structural member we are constructing. So how the admixture should be? The admixture should not impair durability. Durability means the lifespan, we can say, how long the structure will give the serviceability criteria. So that should not get impaired due to the addition of admixtures. Admixtures should not combine to form harmful compounds. If at all the admixture having some chemical reactions with the concrete or with the cement, it should not produce harmful compounds. For example, sulfate attack or any other harmful compounds which can induce corrosion or any cracks or etc. Next one is it should not increase the risk of corrosion because any chloride content in an admixture will induce the corrosion. So chloride content has to be independently tested to avoid this risk of corrosion. Now the admixture can be divided broadly into mineral admixtures and chemical admixtures. Mineral admixtures, the examples are fly ash, silica fume, rice husk ash. These are the mineral admixtures. Now coming to chemical admixtures, there are 4 different types of chemical admixtures. First one is the accelerating admixture, which is nothing but it can accelerate the setting time of the cement, or setting time we can say. It can reduce the hardening and setting time. The examples are calcium chloride, fluorosilicate, triethanolamine. And the next one is retarding admixture. Retarding means the opposite of accelerating. It can increase the time of setting or hardening. Hardening time it can increase. Example, sodium tartarate, tartaric acid. You can remember by TAR. Here is also tartarate, TAR, tartaric acid. Retarding admixture, examples of retarding admixture is sodium tartarate, tartaric acid. Next one is a water reducer or plasticizer. The name itself says the water content can be reduced in the concrete mix. So example is this, calcium lignosulfate, sulfate. Air entraining admixture. Air entraining means what? We can induce the voids between the concrete constituents. Air entraining admixture. Example, aluminum powder, neutralized Vinzol resin. Now let's move on to some facts about admixtures. Some facts we can see. Air entrainment admixture. By air entraining the concrete, there is some reduction in the compressive strength. How much? For each percentage increase in air content, the compressive strength reduces approximately by 1.4 MPa megapascal. For each percentage increase in air content, there is a reduction in 1.4 megapascal strength of a concrete. In case of air entraining admixture. In case of super plasticizer, it can permit the reduction in water up to 30% without affecting the workability. Workability in sense, we can say this slump value without affecting the workability for the same amount of cement. This is about some facts on admixtures. Let's move on to concrete and reinforcement. First, we'll see about the reinforcement. What is reinforcement? It is nothing but the steel we are providing at the bottom of the concrete to take the tension. So the reinforcement or the steel should have the Young's modulus of elasticity equal to 2 into 10 power 5 megapascal irrespectively of any grades. The steel should have the elasticity 2 into 10 power 5 MPa megapascal or Newton per mm square. The 3 grades widely used are Fe250, that is nothing but mild steel, Fe415 and Fe500. Nowadays, Fe550 and TMT, thermomechanically treated bars, also available. So this is all about the some points on reinforcement. Let's move on to concrete. What is concrete? We have already seen. It is a mixture of some constituents, aggregates, binding material, water, etc. Sometimes admixtures can be used. So the concrete can be denoted by the strength of concrete can be denoted by its characteristic strength, and it is denoted by FCK, F suffix CK. The tensile strength or flexural strength, we can say it's given by FCR is equal to 0.7 root FCK. What it means? The tensile strength means the bending strength, we can say flexural strength at the bottom of the member, which will be subjected to tension, is very meager. For a concrete, the tensile strength is very meager. We can say about a tenth of compressive strength. If you take M20 grade of concrete, the tensile strength will be around approximately 2 Newton per mm square, 1 by 10th of 20. So it is rough or thumb rule, we can say. The FCR value, the tensile strength value, can be found exactly by using this formula specified by IS code, 0.7 root FCK. There are three types of concrete. First one is the ordinary concrete, second one is standard, third one is the high strength concrete. Ordinary concrete means the concrete grades corresponding to M10 to M20. Standard concrete means the concrete grades corresponding to M25 to M55. High strength means more than M60 or 60 Newton per mm square. High strength concrete as specified by IS 10262 as well as IS 456. Now the question for you is, what is the approximate ratio of strength of concrete at 7 days to that at 28 days curing? If you want to take the 7 days strength in calculation, how much amount of 28 days you will take? That is how many ratio or how many percentage of 28 day strength will you take for 7 days strength? Or the question directly is there, what is the approximate ratio of strength of concrete at 7 days to that of 28 days curing? The answer is 0.65. This value is found by the scientists Minus and Young. The ratio of strength of concrete at 7 days to that of 28 days curing is nothing but 0.65. Now we have seen about the cement, aggregates, water, admixtures, and some facts on reinforcement and concrete. Now let's move on to some important formulas with concrete. First one is the first property is the modulus of elasticity. E value can be found by this formula. This formula is specified by IS 456. EC is equal to 5000 root FCK. It may differ by around plus or minus 20%. So EC is 5000 root FCK. Next formula is the flexural strength or tensile strength, as we have already seen. FCR is equal to 0.7 root FCK. Next one is the shrinkage and creep. Total shrinkage strain is approximately equal to 3 into 10 power minus 4 or 0.0003. Total shrinkage strain is 3 into 10 power minus 4. The creep coefficient or phi value is the ratio of ultimate creep strain to the elastic strain. So by providing creep coefficient value to the in the calculation of modulus of elasticity, we can give the effective modulus of elasticity as EC divided by 1 plus phi. This formula usually refers to the long-term elastic modulus, and this formula usually refers to the short-term elastic modulus. So E is equal to 5000 root FCK is nothing but the short-term elastic modulus. Effective modulus of elasticity is equal to EC by 1 plus phi is nothing but the long-term elastic modulus with the inclusion of creep coefficient or creep criteria. Next we move on to concrete workability, durability, and exposure condition. What is workability? With which is we can handle the concrete is nothing but the workability. So IS code specifies 5 degrees of workability. First one is very low, second one is low, third one is medium, high, fourth one is high, fifth one is very high. These are based on the slump values. Very low degree of workability means the slump value will be less than 25. This slump value or this degree of workability is used widely in highway construction, in cement, concrete, or rigid pavements. Next one is low workability, 25 to 75 mm for mass concreting purposes. Medium degree, 50 to 100 mm slump used for heavily reinforced section of slab where pumping is required. Whenever there is a pumping, we want to use highly workable, so medium degree of workable concrete whenever there is pumping is required. High degree of workability, that is 75 to 100 mm slump, is used in situ piling, or piling means pile foundation. We can use high degree of workability. With low degree of workability, if we use the piling, there will be a segregation, or there will be less compaction. So high degree of workability has to be used in case of piling purposes. For very high, for in situ piling using Tremy pipe means a pipe with, into which the concrete is poured so that piling can be done. So very high degree of piling of about 100 to 150 mm slump value is used for using piling using Tremy. Next one is the durability. Durability is affected by the surrounding cover to the embedded steel, type and quality of constituents, what is that quality, and the water cement ratio, workmanship, shape and size of member. This is obviously the one which affects the durability or the lifespan of the member or structure. Next one is the exposure conditions. Like 5 degrees of workability, there are 5 exposure conditions specified by IS code. First one is a mild, second one is a moderate, third one is severe, fourth one is very severe, fifth one is extreme. Mild exposure conditions means the concrete member is protected against weather. Moderate means the concrete member is subjected to severe rain, saturated salt air, continuously under normal water, contact with non-aggressive soil. This is all about the moderate exposure conditions. Severe means there will be severe rain, alternate wetting and drying, immersed in seawater. This will come under severe exposure conditions. Very severe means there will be seawater spray in case of coastal areas, and there will be some corrosive fumes, severe freezing and thawing condition, aggressive soil. Extreme exposure conditions refers to the tidal zone, when the structural member is subjected to tidal zone, aggressive chemicals, etc. So these are the exposure conditions: mild, moderate, severe, very severe, extreme. By using this exposure conditions, we can arrive the minimum nominal cover to each structural member. Next one is the 3 constituents that adversely affects. What are the 3 constituents? We have already discussed about this: chloride, sulfates, alkali aggregate reaction. Chloride induces corrosion, sulfate inhibits the or affects the hydration of cement. Alkali aggregate reaction also affects the chemical properties of cement. So 3 constituents that adversely affects are chloride, sulfates, alkali aggregate reactions. So before moving to concrete mix proportioning, let's have some questions. First question is, by restricting the minimum cement content and maximum water cement ratio, can we meet the requirements of more durable concrete? Yes or no? By restricting the minimum cement content and maximum water cement ratio, can we meet the requirements of more durable concrete or not? Durability means we are increasing the lifespan of the structure by restricting the minimum cement content and maximum water cement ratio. Is it possible or not? If your answer is yes, you are absolutely right. And next question is, increase in VB time increases that the workability is high. Workability can be measured using some methods such as VB time method, compaction factor method, slump test method, etc. So in this method, increase in VB time increases that the workability is high. When the concrete will have the high workability? When there is some high water content, and the concrete is like in a flowy condition, etc. So increase in VB time. In VB actually what happens is the concrete is revolved inside in a drum so that it spreads. So high time required for high workable concrete or low workable concrete. Obviously, low workable concrete will require the high time to get spread out in the drum by some revolutions. So answer for this is false. Increase in VB time indicates that the workability is low. So next, moving to concrete mix proportioning. What are the constituents in the concrete? Cement, coarse aggregates, fine aggregates, water, and admixtures sometimes. What are all the types of mix we can have? Design mix and nominal mix. When will the design mix can be used? Design mix means we are calculating actually for the proposed concrete member. So when we can design a mix for only M20 and above? For less than for up to M20 grade, we can use the nominal mix as given by IS code annexures. Design mix should be or only be used for concrete grade having M20 and above. We can see some ratios of nominal mixes. For M5 grade, it is 1:5:10. For M7.5, it is 1:4:8. Actually, the last ratio will get decreases by 2. Middle ratio, middle value get decreases by 1. First will be 1. Cement M10 gives the ratio of 1:3:6. M15 1:2:4. M20 is 1:1.5:3. It is the most important one. M20 grade. M25 1:1:2. M30 1:1:3. These are all some nominal mixes which are already been designed. It's already been given in IS code. How the concrete is produced? It is the production is done in the batching plant. The formwork we are using is has to be removed after 16 to 24 hours of concreting. The vertical formwork for these beams and columns, walls, removed after 16 to 24 hours of concreting. Nominal mix ratio refers to the cement is to sand or fine aggregate is to coarse aggregate. Now next we'll move on to the how the reinforcement is assembled. Assembly of reinforcement and the concrete how the in this slide. The actual cover to rebar should not deviate from required nominal cover by 0 to plus 10 mm. This is the cover distance. The cover distance is specified on the basis of exposure conditions in IS 456 code. For footing, it should not be less than 50 mm, and other members it is based on the exposure conditions. So the actual cover to rebars that we are provided should not deviate from required nominal cover. Nominal cover is specified in IS code by 0 to plus 10 mm. What does it mean? What does it mean? The nominal can be greater than the actual. Sorry, the actual cover can be greater than the nominal cover, but in no case it shall be less than the nominal cover. That's why it can be deviated by 0 to plus 10 mm, not plus or minus 10 mm. So assembly of reinforcement is nothing but we are specifying the cover for the concrete and steel. Now next is the transporting and handling of concrete. How that concrete is transported and how it is to be handled. Common ways of transporting as specified in IS code are head load, dumper, transit mixer. Transit mixer means we have already seen in the road. Transit mixer, or you can see the ready mix concrete RMC plant, and fourth one is the pumping in case of piling, etc. The permissible free fall of concrete is 1.5 meter. 1.5 meter. The permissible free fall of concrete is 1.5 meter. Now next we'll move on to the compaction and curing. What is meant by compaction and what is meant by curing? Moist curing means the exposed surface of concrete shall be kept continuously in a damp or wet condition by ponding or by covering with a layer of sacking or canvas for at least 7 days from the date of placing of concrete. Steam curing can also be adopted for high strength concrete. And the most important fact is railway sleepers are steam cured. Steam curing will be coming under moist curing. What is membrane curing? Curing compound may be used in the line of moist curing. It is also applied to all exposed surfaces of the concrete as soon as possible after the concrete has set. It prevents evaporation of concrete water content. It is nothing but the membrane curing. So now let's move on to next slide. Is there any difference between test samples and test specimens? Just think about it. We can see the answer later on. Now we move on to the frequency of sampling. IS code. The class number is 15.2.2. The minimum frequency of sampling of concrete of each grade shall be in accordance with the following. This will be used for minimum number of samples that should be used in accordance with the quantity of concrete in the work in meter cube. For example, if you use the 7 meter cube of concrete, if we have to use two numbers of samples. If we use the 55 meter cube quantity of concrete, we want to use the four number of samples plus one additional sample for each additional 50 meter cube are part thereof. So this frequency has to be used in accordance with the IS 456. The individual variation between specimen should not be more than plus or minus 15% of average. For example, we have three 150 mm cubes. 3 cubes are tested. So we have obtained we have observed the values, strength values of for all the 3 cubes. The strength values between those 3 cubes should not vary 15% of the average of 3 cubes. If it's so, the sample has to be discarded and try another sample. So what is the acceptance criteria? Samples. First one is the mean strength determined from group of 4 consecutive test results satisfy the appropriate limits in this table. This table number 11 of IS 456-2000 specifies that how much mean strength determined from group of 4 consecutive test results will satisfy this following limits. So this table has to be used to see the characteristic compressive strength compliance requirement. It is in the table 11 of IS 456. For example, assume 100 meter cube of M25 concrete that has been placed at the site in 30 days as below. This is a table, and in the above table, column 1 represents the days of concreting at site and column 2 represents the volume of concreting on that day. For first day, the quantity is 28 meter cube. For the 7th day, the quantity is 45, and so on. Column 3 represents the number of samples taken on the day of concreting only. Since each sample is having 3 specimens, so column 4 represents number of specimens taken during concreting. So column 4 means sample number 1. So one sample refers to the 3 specimens taken during concreting. Each sample has been given a number so as to represent which sample is that. Column 6 is the compressed strength of sample, average of 3 sample, 3 specimen of each sample. This is some of the example we can say. For the acceptance criteria for this problem, mean of any 4 non-overlapping has to be taken. So non-overlapping here means take either 3, 4, 5, 6. Sample number 3, 4, 5, 6. This is the mean. This is the non-overlapping member. So non-overlapping samples. We can also take either 5, 6, 7, 8. We can take either 3, 4, 5, 6, or we can take 5, 6, 7, 8. But not 1, 2, 5, 6. These are not the overlapping. 1, 2, 5, 6 are not are overlapping. Actually, we have to take any 4 non-overlapping test sample numbers. So non-overlapping means 3, 4, 5, 6, and or we can take 5, 6, 7, 8 numbers, but we should not take number 1, 2, 5, 6, and or we can say 3, 4, 9, 10. 3, 4, 9, 9, 10. We should not take these numbers. So average of sample numbers, if we take 5, 6, 7, 8, if we take the average of these values, it will give around 29.25. If you calculate accurately, it will come around 29.25. That 29.25 has to be compliance in this table. 29.25 greater than or equal to FCK plus 0.825 into standard deviation. Standard deviation value has to be taken from table number 8 of IS 456 for the respective concrete grade. For M20 grade, it is 4. 29.25 greater than or equal to FCK plus 0.825 into 4 will give the FCK value as 25, and it will give the FCK value as 28.3 or FCK plus 3. Actually, FCK is 25. 25 plus 3 is 28. So whichever is greater. From the first this formula, we have some 28.3. For second formula, 28 Newton per mm square. So value of compressive strength given in column 6 is greater than FCK minus 3. This column has to be in compliance with. So FCK minus 3. FCK is 25. 25 minus 3 is 22 Newton per mm square. So this is greater than. So actually, this 28.3 we have got in by using this formula is greater than FCK minus 3. So the concrete is acceptable. The samples taken are acceptable. This is some illustrative example we can refer to. So coming to next criteria after material and material, we have cement, concrete, aggregates, water, admixtures. From section 2, we have again inspection and testing. We have completed material. Workmanship is nothing but it depends on the mason and the contractor who are building the who are actually constructing workmanship. That depends on the manpower. And the last part is of this section 2 is the inspection and testing. How do you inspect the structures after it is being constructed? There are some two test methods. First one is destructive test and second one is non-destructive test. The destructive test refers to the constructed structural member has to be destructed in the laboratory or some in a site itself, so that we can get an idea about the strength or constituents changes in the member. There are two types: core test and load test. Non-destructive test means there is no destruction or partial destruction in the structural member. There are two tests in the non-destructive type: rebound hammer test test and ultrasonic pulse velocity test. We will see about it. The non-destructive test may be performed directly on the in situ concrete without the removal of a sample. These tests do not impair the intended performance of the element or member being tested. So non-destructive tests may be directly performed in the in situ concrete, and they also include methods which cause localized surface zone damage and may be called partially destructive. As I have already told, non-destructive test can be partially destruction. The ultrasonic pulse velocity method is a non-destructive method, a non-destructive test for hardened concrete which is already built, which basically involves the measurement of velocity of electronic pulses passing through the concrete from a transmitting transducer to a receiving transducer, some electronic devices. And the question is, does the velocity of pulse passing through the concrete depend on the geometry of the component or not? The geometry refers to the rectangular or any other. If you can see the circular columns, you can see the rectangular beams, etc. These geometry does it affect the velocity of pulse passing through the concrete or not? The answer is no. The velocity of pulse primarily depends on density and elastic properties of concrete only. It does not depend on geometry of that component. So the concrete constituent mainly affects the velocity of pulse in case of ultrasonic pulse velocity test. So coming back to the question, is there any difference between test samples and tests? The answer is yes, there is a difference between test samples and test specimens. A test sample consists of 3 test specimens. Test specimen means one concrete cube of standard dimension 150. This 150, one number of concrete refers to the test specimen that has a standard dimension of 150 mm. So a test sample refers to 3 test specimens. So this is all about the section 2. We are at the end of the section 2. In section 2 we have seen about the material like cement, aggregates, water mixture, etc. And at the last we have seen inspection and testing. Now we shall move on to section 3, general design concepts. What are all the bases for design? Obviously there should be safety, serviceability, etc. There are 5 requirements. The first one is safety, second one is serviceability, durability, economy, aesthetic. Serviceability will come under some limit state of serviceability, deflection, cracks, shrinkage. These will be coming under serviceability criteria. Safety, in case of safety, limit state of collapse, flexure, torsion. This will come under safety. We have to design for safety, serviceability, and durability, economy, aesthetic will be coming under the type of material we are using. And what are all the loads and forces has to be considered? First one is the dead load or dead weight, we can say, weight of the member or self weight of the member, live load or imposed load, wind load, earthquake load. We usually take either wind load or earthquake load. We do not take simultaneously the wind load and earthquake load in calculations. Another some type of load are snow load, an effect due to shrinkage, creep and temperature, foundation movement, erection load, vibration, impact, fatigue, etc. And the unit weight of RC, that is reinforced cement concrete, may be taken as 25 kN per meter cube, and the and the unit weight of plain concrete may be taken as 24 kN per meter cube. The design load is the load. It should be taken for design of any structural member. If we give the load for the design purposes, then that load can be called as a design load. It is a load to be taken for design of any structural member. In case of working stress method, it is the characteristic load. We have to say that load as characteristic load but not the design load as in limit state, because partial factor of safety is multiplied for limit state design, but in case of working stress method we are using factor of safety, not the partial safety factor as in the case of limit state method. Now let's learn facts on the fire resistance. A building is made fire resistant by using suitable construction material and providing appropriate cover to steel. The minimum width of beam that should be used for fire resistant building is 200 mm. This is specified by IS code. Now let's move on to the analysis part. Considerations in case of beam. First, we shall see about the effective span for simply supported beam. It is given by L effective is equal to clear span plus effective depth, or clear span plus width of the member. Width of the member. Next is the continuous beam. Actually, this minimum of this has to be taken as the effective length, LC plus D or LC plus B, whichever is lesser. Next one is the continuous beam. If the width of the support is less than 1/12 of the clear span, then the effective span is same as this formula. If more than 1/12 of the clear span or 600 mm lesser of 2, then the effective span will be given by this formula notation. L effective should be less than L clear spans plus half of the effective depth, or LC plus B by 2, whichever is lesser. It is in the case of continuous beam. In the case of cantilever, effective span, we shall see. Effective span will be equal to clear span plus D by 2. For frames, center to center distance is used. There is no formula for frames. For simply supported beam, it is LC plus D or LC plus B. For continuous beam, it depends on the width of support and clear span. If it is if the width of support is less than 1/12 of clear span, the effective span is same as that of simply supported, or else there is some formula LC plus D by 2 and LC plus B by 2, whichever is lesser. And cantilever beam, this formula, and for in case of frame, center to the center distance is used. And what are the kinds of sections that are available or that are used in the design purposes? Grass section, transformed section, cracked section. What is meant by cross section? The cross section of the member ignoring reinforcement. If we ignore the reinforcement, that is called cross section, and the concrete cross section plus the area of reinforcement transformed using modular ratio is called the transformed section. Modular ratio is nothing but the ES by elastic modulus of steel divided by elastic modulus of concrete. So if we use modular ratio to transform the section as same material, so that section is known as the transformed section using modular ratio. Cracked section, the area of concrete in compression plus the area of reinforcement transformed on the basis of modular ratio is the cracked section. Now coming to the arrangement of imposed loads, should be arranged for maximum hugging moment and maximum sagging moment. IS code specifies that consideration may be limited to combinations of the following. First one, design dead load on all spans with full design live load or imposed load on two adjacent spans plus alternate spans for maximum hugging moment at the support B as shown below. If you see the diagram, it will be clear enough. The live load has to be placed in such a way that it should be located on two adjacent spans and the alternate spans for the maximum hugging moment at this support B. For in case of maximum bending moment in span, that is maximum positive or maximum sagging bending moment in span, the following will be followed. Design dead load on all spans with the full design live load. Design dead load will be supposed on all spans with full design live load on alternate spans for maximum sagging bending moment in between support A and B as shown below. So this is the arrangement of imposed load if you want to find the maximum sagging bending moment in the spans fan AB, for example this. So this is about the arrangement of imposed loads. So next we shall move on to bending moment coefficients. Number 12 of IS 456-2000. For the type of load, dead load and imposed load, we shall use the bending moment coefficient as per this table number 12, and for shear coefficients, table number 13 has to be used. For example, if the type of load is dead load and imposed load fixed, span moments will be multiplied for near middle of end span by 1 by 12, at the middle of interior span 1 by 16. This will be followed for bending moment coefficients and as well as the shear coefficients. Now we shall move on to the critical sections. What will be the critical section for moment as per IS 456? For monolithic construction, the moments computed at the face of the support shall be used in the design of members at those sections. Those section means the moments computed at the face of support shall be used in those section monolithic construction members. And for critical section for shear, when the reaction in the direction of applied shear introduces compression into the end region of the member. When the reaction in the direction of the applied shear introduces compression into the end region of the member, sections located at a distance less than d from the face of the support may be designed for the same shear as that computed at distance d. So this is all about the typical support conditions for locating factored shear force. This is a critical section, that is depth d from the face of the support, mid of the face of the support, this section, critical section, and also this effective depth. When there is heavy load, the load should be located less than 2 times the effective depth of this bracket from the face of the column support. Now we shall move on to general design beams. The effective depth is the distance between the centroid of area of tension reinforcement and the maximum compressive fiber. The effective depth means the distance between the topmost compressive fiber to the center of area of tension reinforcement. If there is some 2 line or 3 line of reinforcement, the centroidal or the CG of those tension reinforcement has to be calculated, and up to which we can find the effective depth, up to which the depth is called as the effective depth. A slab which is assumed to act as a compression flange of a T-beam or L-beam must be casted monolithically with the web or bonded firmly together. A slab which is assumed to act as a compression flange of a T-beam should be cast monolithically. It should not be casted separately. It should be cast as a monolithic member with the web or bonded firmly together. Effective width of flange may be taken as the following, but in no case greater than the web plus half the sum of the clear distance to the adjacent beams on either side. Now we shall see some important parts of design of beams. First one is T-beam. The effective width of flange, the width of flange of T-beam shall be calculated by using this formula L0 by 6 plus BW plus 6 DF. Here BW is the width of web, DF is the thickness of flange or depth of flange, L0 is the distance between the points of contrafracture. For L beam, L0 by 12. For L beam, the width of flange will be equal to L0 by 12 plus BW plus 3 DF. And for isolated sections, isolated T-beam, the formula is this. And for isolated L-beam, the effective width of flange will be calculated using this formula. So these are important formulas that can be asked in any examinations. So some other points are as follows. For continuous beams and frames, distance between point of zero moments in the beam may be assumed as 0.7 times the effective span. For continuous beams and frames, the distance between zero moments or the point of control fracture in the beam may be assumed as 0.7 times the effective span. The final deflection due to all loads, including effects of temperature, creep, and shrinkage, and measured from the cast level of the supports of floors, should not normally exceed effective span by 250. This is the most important point which can be asked in any examinations frequently. The final deflection due to all loads, including such temperature, creep, shrinkage, etc., shall not normally exceed effective span divided by 250. Another deflection criteria is the deflection due to effects of temperature, creep, and shrinkage after erection of partitions and the application of finishes should not normally exceed span by 350 or 20 mm, whichever is less. So these 2 points are most important in case of competitive examinations purposes and in case of any interviews. Now we shall move to deflection criteria and as well as the slenderness ratio. So these are the basic values for the vertical deflection criteria. These values are the ratio of span to effective depth. For a span up to 10 meter. For cantilever it is 7. For simply supported it is 20. For continuous support it is 26. For slenderness ratio, to ensure lateral stability, clear distance between lateral restraints should not exceed. In case of cantilever, it is 25 times the width or 100 b square divided by effective depth. In case of simply supported, it is 60 b or 250 b square by d. In case of continuous, it is same as that of simply supported. Whichever is less we have to take, whether it is 25b or 100b square by d, whichever is less you have to take that value only. So this is all about the vertical deflection and slenderness ratio for beams. Now we shall move on to another member called slabs. In case of slab, the shorter of two spans should be used for calculating the span to effective depth ratios. First, the slab has to be designed for deflection criteria, L by D ratio. For calculating those L by D ratio, we have to use only the shorter of two spans only. That is, if we are supposed to have Lx and Ly, the shorter of two spans should be used for calculating the deflection ratio, span to effective depth ratios. For two-way slabs of shorter span up to 3.5 meter with mild steel reinforcement, the span to overall depth ratio given below is generally assumed to satisfy vertical deflection limits for loading up to 3 kN per meter square. For simply supported slab, this span to overall depth ratio is about 35. In case of continuous slab, this span to overall depth ratio is 40. For high strength deformed bars of grade Fe or 415, these values can be multiplied by 0.8. That is, we can take 80% of these values only for in case of high strength deformed bars of grade some Fe415 or Fe500 something. Now the question for you is, for a continuous slab of 3 meter cross 3.5 meter, the minimum overall depth of the slab is it is a simple calculation based on these 2 points. For a continuous slab means the span to overall depth ratio will be 40. The span will be either 3000 meter or 3000 mm or 3500 mm. So the shorter of two spans has to be used. So 3000 divided by 40 gives answer as 75 mm. So for a continuous slab of this size, 3 meter cross 3.5 meter, the minimum overall depth of slab. Minimum overall depth of slab is 75 mm, which is calculated by 3000 divided by 40. In case they have specified the highest and deformed bar, this value can be multiplied by 0.8. So next, moving on to general design consideration for another member called column, or we can say compression members. Column or strut is a compression member for which the effective length of which exceeds 3 times the least lateral dimension. Column or strut is a compression member, the effective length of which exceeds 3 times the least lateral dimension. If it not exceeds, but it is a compression member, then that is called the pedestal. Both the slenderness ratios of short compression member are less than 12. If it greater than 12, we can call it as longer compression member. But both the slenderness ratio, it is specified, that is Lx by D and Ly by D. Both the slenderness ratios of shorter compression member should be less than 12. If it is more than 12, we can simply say it as a longer compression member. So this is a typical cross section of a column. This is the breadth or width of the column. This is the depth, overall depth, and I-axis here it is greater than IYY. For this configuration, moment of inertia for x-axis is greater than IYY. The unsupported length L of a compression member shall be taken as the clear distance between restraints. This is one of the important points. In case of compression member, the unsupported length of a compression member shall be taken as the clear distance between restraints. Now we shall see some codal provisions for. First, we shall see the slenderness limits. The unsupported length L of a compression member shall be taken as the clear distance between end restraint, as we have seen already. If in any given plane, one end of a column is unrestrained, means something like a cantilever structure, its unsupported length L shall not exceed 100 b square by d. As we have already seen, in case of slenderness limits in beam, cantilever beam, it is about 100 b square by d. Here the same criteria has been followed. If the one end of a column is unrestrained, its unsupported length shall not exceed 100 b square by d. The unsupported length in case of unsupported length between restraints shall not exceed 60 times the least lateral dimension of a column. This is some criteria for slenderness limits. Next, we shall move on to minimum eccentricity. This formula is very important for calculation purposes. All columns shall be designed for minimum eccentricity. E minimum is equal to unsupported length by 500 plus lateral dimension divided by 30 or 20 mm, whichever is more. This is required for the axial transfer of load. Axial load transfer, this minimum eccentricity criteria has to be specified or followed. Next one is the reinforcement. Simultaneous usage of two different grades is permissible. Bars may be arranged singly. It can be arranged in pairs or in group of 3 or 4 bars bundled in contact. In case of bundled bars larger than 32 mm dia, those should not be bundled. If you use the bundled bars, if you use the bars of larger than 32 mm diameter, that bars shall not be bundled except in column. So reinforcement, how will be the reinforcement? Why the reinforcement has to be provided? Development of stress criteria, development length of bars. We have the development length, and we have to provide some anchoring length of the bars. So now we shall see the reinforcement detailing and its requirements. Development length, it is given by the formula LD is equal to 5 sigma s divided by 4 tau BD. 5 is the diameter bar, sigma is this strength of steel divided by 4 into tau BD. Design bond stress for deformed bar shall be 60% higher than design bond stress for plain bar. Tau BD is the design bond stress, and it can be increased by 1.6 times in case we are using deformed bar. And for bar in compression, the value shall be further increased by 25%. If the proposed reinforcement is for compression, the for bar in compression, this tau BD value can be increased by 1.25 times. If it is of for Fe415 deformed bars, it can be of 1.25 into 1.6 into tau BD. So how much value can be increased in case of this criteria? So we have seen the development length, and we shall move on to the anchorage length. This is the anchorage of the reinforcement, how the bending or hooks can be provided. It is the representation for standard 90-degree bend, and it is the representation for standard U-type hook. Anchoring is provided by bends and hooks at the end, which is equivalent to resistance provided by straight bars. The anchorage value of bend is 4 times the diameter of bar for each 45-degree bend. 4 pi for each 45-degree bend, subject to a maximum of 16 times the diameter of the bar. This is the criteria for anchorage value. And in case of U-type hook, the anchorage value will be 16 times the diameter of bar. So now your question is, will anchorage length of bend and hooks be considered in case of compression or not? In case of compression, anchorage will be considered or not. Anchorage means nothing but some anchorage is provided when there is some pulling force. There should be enough bond strength to resist the pulling force. So that we are providing the anchorage length. So in case of compression, it is necessary to provide the anchorage length? No. The answer is no. In case of compression, we are not providing anchorage length in the form of bends or hooks, whatever may be. And what is the difference between the two lengths, development length and anchorage length? What is the difference between development length and anchorage length? Development length means we are increasing the length to the support or some we are again inducing the bond stress by using development length criteria. In case of anchorage length, we are providing for it for pulling stresses. We are providing to control the pulling stresses. So development length, it is used for resisting pulling force. Anchorage length is provided only at supports. So anchorage length is provided only at supports. Development length is provided to resist the pulling force. This is the difference between the development length and anchorage length. Now we shall move on to the curtailment of structural members. In general, reinforcement shall extend beyond the point at which it is no longer required to resist flexure. Whenever there is no need of taking the tension, up to which we should extend the tension reinforcement for a distance equal to the effective depth D of the member, or 12 times the diameter of bars, whichever is greater, except at simple support or end of a cantilever. For positive moment reinforcement, at least 1/3 of positive moment reinforcement in simple members and 1/4 continuous members shall extend along the same face of the member into the support to a length equal to development length divided by 3, 1/3 of development length. In case of negative moment reinforcement, the same will be followed. At least 1/3 of negative reinforcement moment at support shall extend beyond the point of inflection for a distance not less than effective depth of member, or 12 pi or by 16th of clear span, whichever is greater we have to use in case of negative moment reinforcement. Now in case of bundled bars, Bars in bundles shall terminate at different points spaced apart by not less than 40 times the diameter of bar, except for bundles stopping at a support. These are some provisions or some specifications provided in IS code. Now we shall see some more important points on positive moment reinforcement and negative moment reinforcement. At simple supports and at points of inflection, positive moment tension reinforcement shall be limited to a diameter such that development length computed for design stress by class number 26.2.1 does not exceed this value m1 by v plus L naught. What are all these symbols or this symbols describe? M means the amount of resistance of the section, assuming all reinforcement of the section to be stressed to FD. FD value design stress, it is equal to 0.87 Fy. V is the shear force. L naught is the sum of anchorage beyond the center of support, equivalent anchorage of any hook or mechanical anchorage, a simple support, and a point of inflection. L naught is limited to effective depth of members or 12 phi, whichever is greater. Phi is the diameter of bar. And in case of negative moment reinforcement, this is the development length, which shall not be less than the development length. The negative moment or the hogging moment. Hogging moment diagram is this. dr12 phi or 1 by 16th of the clear span that we have already seen in the previous slide. This is all about the positive moment reinforcement and negative moment reinforcement. Now we shall move on to the splices in. It is recommended that the splices in flexural members should not be done at sections where the bending moment is more than 50% of the moment of resistance and not more than the half of the bars shall be spliced at the section. Splicing is nothing but this diagram only. The members has to be connected, the steel bars has to be connected to make the required length of the structure. It is recommended that splices in flexural members, that is bending members, should not be done at sections wherever the bending moment is more than 50% of moment of resistance and not more than half of bars shall be spliced at a section. Not more than half of bars, half the bars shall be spliced at a section. Now lap splices. Lap splices shall not be used if diameter of bar is greater than 32 mm. For larger dia, bars can be welded. Instead of tying the bars like this, we can weld the bars, we can weld mechanically in case of bars of larger diameter. Lap length including anchorage value in flexural tension shall be development length or 30 times the diameter, whichever is greater. It is a lap length which specifies the lap splices. For direct tension, it is for flexural tension. In case of direct tension, it shall be 2 times development length or 35, whichever is greater. Straight length of lap shall not be less than 15 times the diameter of bar or 200 mm. This is the most important point, asking frequently in various examinations. Straight length of lap shall not be less than 15 times diameter of bar or 200 mm. The lap length in compression shall be equal to the development length in compression, but not less than 24 pi. Lap length in compression shall not be less than 24 pi. Lap length shall be calculated on the basis of diameter of smaller bar only, not on the basis of larger bar. It should be calculated on the basis of smaller bar. This is all about the splices in reinforcement. Now let's move on to the distance between bars. Maximum distance between bars in tension, and then we shall move on to the nominal cover. First, for beam, the horizontal distance between parallel reinforcement bars near the tension face of the beam shall not be greater than the following. In case of Fy, Fp 250 mild steel, the clear distance between bars will be maximum 300 mm. In case of Fe 415, clear distance between bars maximum 180 mm. it should not be greater than this value. In case of 500, Fe 500, it is 150 mm. For slabs, the horizontal distance between parallel main bars shall not be more than 3 times the effective depth 3D or 300 mm. Horizontal distance against shrinkage and temperature shall not be more than 5D or 300 mm. This is the criteria for slabs. And now we shall see about the nominal cover. Minimum values of nominal cover for different structural member depends upon exposure condition because cover is directly related to the durability of structure. This point is already discussed in the exposure conditions topic. So for a mild exposure, nominal cover is 20 mm, moderate it is 30, severe it is 45, very severe it is 50, for extreme it is 75 mm. For footings, invariably the minimum nominal cover shall be 50 mm. This is all about the maximum distance between bars in tension and nominal cover. Now let's move on to requirements of reinforcement. What are all the requirements of reinforcement? How much minimum, how much is the maximum? We shall see about it. For tension reinforcement, the minimum reinforcement or minimum area of steel reinforcement shall be greater than 0.85 BD divided by Fy. B is the width of member, D is the effective depth, Fy is the steel stress in steel, yield stress in steel. Maximum, it should not be greater than 4% of grass area or 0.04 of B into overall depth. It should be less than or equal to 0.04 B into D. It is in the case of tension reinforcement. What will be in the case of compression reinforcement? Is there any minimum criteria for compression reinforcement? No, there is no minimum criteria for compression reinforcement. There is only a limit for maximum. Maximum is the same as the tension reinforcement, as nothing but the 4% of grass area. And coming to side face reinforcement, when it should be provided, when the depth of web on a beam is greater than 750 mm, side face reinforcement shall be provided along the two faces. The total area of such reinforcement shall not be less than 0.1% of webbed area and shall be distributed equally on two faces at a spacing not exceeding 300 mm or web thickness, whichever is lesser. This is for side face reinforcement. It is only provided when the depth of web in a beam is greater than 750 mm. Now just we move on to the transverse reinforcement. The maximum spacing of transverse reinforcement measured along the axis of the member shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups at 45 degrees. This is in case of transverse reinforcement, and in no case the spacing shall be greater than 300 mm. And what will be the criteria for shear reinforcement? The minimum will be given by ASV, minimum shear reinforcement area, divided by B into SV is the spacing, shall be greater than or equal to 0.4 divided by 0.87 Fy. And this Fy value should not be more than 415 Newton per mm square. So now it's time to question you, why minimum shear reinforcement is provided in the form of stirrups? Is there any specific criteria to provide shear reinforcement in the form of stirrups? Just think about it for some 2 seconds to 3 seconds. Why minimum shear reinforcement has to be provided in the form of stirrups? The answer is, to resist principal tension, we are providing minimum shear reinforcement. The section at which the inclined crack in beam without shear reinforcement is formed first is taken as the shear strength of concrete. Actually, shear strength of concrete is nothing but the section at which the inclined crack in beam without shear reinforcement is formed, as there is a difference between loads corresponding to the first crack and ultimate failure is very less. Formation of such crack occur when the principal tensile stress reaches the tensile strength of concrete. This principal tensile principal tension reaches the tensile strength of concrete, then the crack will occur. At the midspan of a simply supported beam subjected to UDL, or where shear is small and bending stress is large, the direction of principal tensile stress is flat and is nearly equal to the flexural tensile stress. So this will cause flexural cracks nearly vertical to the axis of the beam. Usually this crack will be initiated when half of tau c, that is critical shear, is less than nominal shear is less than tau c. So minimum shear reinforcement has to be provided to prevent flexural crack due to principal tension. So now let's move on to other reinforcement, slab reinforcement, columns reinforcement. Minimum slab reinforcement has to be provided to take care shrinkage and temperature effect, not to resist the moment of resistance or any other. To take care shrinkage and temperature effect, we have to provide minimum slab reinforcement. In case of mild steel, it is greater than 0.15% of total cross-section area. In case of deformed bars, the minimum reinforcement shall be 0.12% of total cross-section area. What will be the maximum? It is about 1/8 of the total thickness of the slab. So this is about the minimum and maximum reinforcement for slab. Now let's move on to columns. Columns, in case of column, there is longitudinal and transverse. So first we shall see about the longitudinal reinforcement. The minimum should be 0.8% of gross area based on area of concrete. It should be the minimum reinforcement should be based on area of concrete only, but not the actual area of column. And in case of rectangular column, minimum number of bars is 4. In case of circular, minimum number of bars is 6. Minimum diameter of bar is 12 mm. For pedestals, 0.15% of cross section area. This is all about the minimum satisfying criteria in case of longitudinal reinforcement in columns. And what will be the maximum reinforcement? It is 6% of gross area, but usually it is limited to 4% because of practical conditions. The spacing should not be more than 300 mm. This is the maximum area of longitudinal reinforcements in case of columns. And in case of transverse, there are two types: lateral ties and helical reinforcement. For lateral ties, the pitch shall not be less than of the following: least lateral dimension 16 times the smaller diameter of bar, or 300 mm, whichever is lesser. Diameter, it shall not be less than 1/4 of the largest diameter, or 6 mm. It is all about the lateral ties, and we shall move on to helical reinforcement. Thus, for the pitch, it shall be less than 75 mm, or 1/6 of the codia, or greater than 25 mm, or 3 times the diameter of helix bar. Whatever the bar we are quoting for is, the diameter has to be multiplied by 3, and that value should not be less than pitch. So pitch shall be greater than 3.5. Diameter of helical reinforcement shall not be less than 1/4 of largest diameter and 6 mm. This is the same as that of lateral ties. So this is all about the transverse reinforcement, and we are at the end of section 3, which is nothing but the general design considerations for various members such as beams, slabs, columns, etc. We have seen every codal provisions which is important for us, such as requirements governing reinforcement detailing, anchorage length, development length, curtailment, positive moment reinforcement, etc. Now we shall move on to section 4 of IS. Section 4 describes the special design requirement for structural members and systems. First we shall see about the walls. First we shall see about the deep beams and flat slabs, and then we can move to the walls. First, deep beams. What is the deep beam? Whenever there is a ratio of effective span to overall depth, that is L by D, is less than 2 for 2 in case of simply supported beam, it can be called as deep beam. In case of continuous beam, that L by D ratio should be less than 2.5. So this is the deep beam. And in case of flat slab, minimum thickness shall be 125 mm, and the critical section for CL shear shall be at a distance d by 2 from the periphery of the column capital or drop panel and perpendicular to the plane of the slab where d is the effective depth of the section. This is all about the deep beams and flat slabs. And next we move on to walls. The minimum thickness of walls shall be 100 mm. Concrete walls. Minimum thickness shall be 100 mm. The eccentricity of the vertical force on the wall subjected to a minimum of 0.05 t, where t is the thickness of wall. So 5% of thickness of wall is the eccentricity of vertical force, which is subjected to the wall. Ratio of effective height to the thickness of wall shall not exceed 30. Ratio of effective height to thickness of wall shall not exceed 30. For wall thickness greater than 200 mm, the vertical and the horizontal reinforcement shall be provided in 2 grids, one near each face of the wall. So this is all about the criteria for concrete walls as a special design requirement of structural members and system. And we shall see more on about the footings. The thickness of footing edge shall not be less than 150 mm. This is the major criteria for footing. Thickness of edge shall not be less than 150 mm. The greatest bending moment has to be used in the design of isolated footings. Section located as for the greatest bending moment, the section has to be located as follows. At the face of column or pedestal or wall for footings supporting monolithic constructed column or walls. Halfway between the center line and the edge of the wall for footing under masonry walls. First one is the monolithic, and next one is the masonry walls, and next one is the gusseted bases. Halfway between the face of the column or pedestal and the edge of gusseted base for footings under gusseted bases. So these are the sections that has to be located to find the greatest bending moment for the design of isolated footings. So what is the critical section for shear? For one-way shear, the critical section will be located at a distance d from the face of the column. In case of two-way shear, it is at a distance d by 2 from the face of the column. So this is about the footings. Load at the base of column. So this formula, actually the bearing pressure on loaded area shall not exceed the permissible bearing stress in direct compression multiplied by a value equal to root of A1 by A2, and this value should not be greater than 2. So bearing pressure shall not exceed the permissible bearing stress in compression. This value has to be multiplied by this factor, and this factor should not be greater than 2. So A1 and A2 will be described as follows. Supporting area for bearing of footing, which is sloped or stepped footing, may be taken as the area of lower base of the largest frustum of a pyramid or cone contained wholly within the footing and having its upper base. The area actually loaded and having side slope of one vertical to horizontal. A2 is the loaded area at the column base. And this point is the most important one. In case of footings, for working stress method of design, the permissible bearing stress on full area of concrete shall be taken as 0.25 FCK. 0.25 FCK in case of working stress method. In case of limit state method, the permissible bearing stresses shall be 0.45 FCK. This is somewhat important for competitive examinations. 0.25 FCK for working stress, 0.45 FCK for limit state. So this is all about the section 4. We are at the end of section 4 of IS 456. So we have seen walls, deep beams and flat slabs, and at the last footings from the section 4 as the special design requirement for structural members and system. Now we shall move on to section 5, structural design, which is method. First, what is limit state? Limit state is nothing but the acceptable limit for the safety and serviceability requirements before failure occurs. Limit state is defined as the acceptable limit for the safety and serviceability requirements before failure occurs. There is limiting value of width of crack. There is limiting value of width of crack. The maximum allowable crack is 0.3 mm for mild exposure condition, 0.2 mm for moderate, 0.1 mm for severe aggressive environment. So this is all about the serviceability criteria, are also a limit state criteria. Maximum allowable cracking should not exceed 0.3 mm in any case. For mild exposure condition, 0.2 mm for moderate, 0.1 mm for severe conditions. The nominal spacing of main bars in slab shall not exceed 3 times the effective depth of slab, that is 3D or 300 mm, whichever is smaller. This is already we have seen under nominal spacing of bars or reinforcement in slabs. 3 times the effective depth of solid slab or 300 mm, whichever is smaller. And now we shall move on to characteristic and design values and then the partial safety factor. What is meant by characteristic strength? The strength at which or below which not more than 5% of test results are expected to fall is the characteristic strength. Characteristic strength means the value of strength of material below which not more than 5% of test results are expected to fall. Design strength of material is given by Fd is equal to F by gamma m. Gamma m is the partial safety factor for material. For concrete it is 1.5, for steel it is 1.15. So this is all about the characteristics and design values. So values of partial safety factor for loads, gamma f for loads. If the load combination is dead load plus live load, then we have to increase those values by 1.5. If the load combination is dead load and wind load, we have to increase this by 1.5. In case of limit state of collapse, in case of serviceability, we should not increase any. It should be multiplied by 1 or it shall be taken as such. In case of load combinations, dead load and live load and wind load or earthquake load, we should not use simultaneously. It shall be multiplied by 1.2. In case of serviceability criteria, it can be multiplied by 0.8. So this is all about the partial safety factor, and then we move on to the limit state of collapse, before which we shall see some 2 points. In no case more than 30% moment redistribution is allowed. IS code specifies that yield line theory or any other acceptable method may be used for analysis of slabs spanning in 2 directions and right angles. Now we shall see about the limit state of collapse fracture. First we will see the assumptions. Plane section remains plane before and after bending is the basic assumption. Maximum strain in concrete is 0.0035 at the outermost compression fiber. Area of stress block is 0.36 FCK XU. FCK is the characteristic strength of concrete. XU is the depth at the compressive action from the topmost fiber. Neural axis depth is the XU. Depth of center of compressive force is equal to 0.42 XU. Tensile strength of concrete is ignored. Stress in concrete at collapse is equal to 0.447 FCK. How this value has come? Actually 0.67 FCK that divided by 1.15 gives the 0.447 FCK. Maximum strain in steel at failure shall not be less than this formula Fy by 1.15 ES plus 0.002. This is a maximum strain at failure which shall not be less than. Now let us see some graphs on the stress strain curve of concrete and how it behaves. This is the actual stress strain curve for concrete. First it varies parabolically, and then after strain of 0.002 it varies in a straight horizontal line. This is the characteristic strength. This is after applying safety factor 0.67 FCK, after applying partial safety factor gamma m 0.67 FCK, which is nothing but 0.447 FCK. This is the stress block diagram. X is the neural axis depth. Up to the compression, the stress varies linear in a vertical direction and then decreases in a parabolically. The compressive force is given by 0.36 FCK XU. This is the strain diagram and this is the stress diagram for a typical rectangular section, and this is the maximum strain 0.0035. At 0.002 the compressive the compressive force acts. It is about 3 by 7 XU and below which 4 by 7 XU. These are we have already seen 0.42 XU, and the C compressive force is equal to 0.36 FCK B XU, and the strain formula should not this strain value should not be greater than 0.002 plus Fy by 1.15 ES. This is a typical characteristic and design stress strain curve for mild steel, but this curve is not suitable for other grades of steel. So this is for Fe415. This is the characteristic curve, and by applying partial safety factor, this is the design curve. So at for example, at 0.004 strain, Ey is equal to 0.002 plus 0.87 Fy by Es. This is 0.87 Fy. This is the value we have taken for this strain. The Xu max by D for Fy for various grades of steel will be as follows. For mild steel, Xu max by D is 0.53. For Fe415 steel, Xu max is equal to 0.448 D. For Fe500 grade steel, Xu max is equal to 0.46 D. D is the effective depth of the member. Now let's see some facts. Whitney's theory is nothing but the ultimate load theory. The ultimate strain in concrete is assumed as 0.3%, and the compressive stress at the extreme edge of the section corresponds to this strain. Whitney has observed that ultimate strain in concrete is about 0.3%. Whitney replaced the actual parabolic stress block by a rectangular stress diagram. We have already seen that the stress block varies linear first, and then there is a parabolic portion. That parabolic stress block has been replaced by a rectangular stress diagram, and that the rectangular stress block has a depth of about 0.537 into effective depth. This is about the Whitney's theory. Now let's move on to the limit state of collapse compression. For compression, for purely axial compression, the strain is assumed to be uniform equal to 0.002 across the section. That is this line, this curve. For purely axial compression, the strain is assumed to be uniformly equal to 0.002 across the section. The strain distribution lines intersect at each other at a depth of 3 by 7 D, 3D by 7, at a depth of 3D by 7 from the highly compressed edge. This point is assumed to act as a fulcrum of the strain distribution line when the neutral axis lies outside the section. This leads to the assumption that the strain at the highly compressive edge is 0.0035 minus 0.75 times the strain at the least compressed edge. So this diagram is important to define the strain in compression member. Strain distribution, we can say. The third curve is the uniformly distributed strain equal to 0.002 across the section, and the strain distribution lines intersect at 3 by 7 D from the highly compressed edge. This is the highly compressed edge, and from 3 by 7th of D, the strain distribution lines will intersect. This leads to the assumption that this value is 0.0035 minus 0.75 times the strain at the least compression edge. Now, how to design a column as a compression member? When the minimum eccentricity as calculated already from class 25.4 does not exceed 5% the least lateral dimension, 5% the lateral dimension, then the member may be designed by the following equation. The minimum eccentricity we have already seen, thus unsupported length by 500 plus lateral dimension divided by 30 or 20 mm, whichever is less. So that value shall not exceed 5% as the list 5% as the lateral dimension. If it's so, then the member may be designed by the following equation. Pu is equal to 0.4 FCK plus 0.4 FCK AC plus 0.67 Fy ASC. Pu is the axial load on the member. FCK is the characteristic compressive strength of concrete. AC is the area of concrete only. That is, we have to exclude the area of steel rebars. Fy is the strength of stress in steel, characteristic stress of compression reinforcement. ASC is the area of compression, area of longitudinal reinforcement of column. ASC. So the strength of compression members with the helical reinforcement satisfying the requirement of core shall be taken as 1.05 times the strength of similar member. If you use the helical reinforcement, this value has to be multiplied by 1.05. Failure of column with helical ties is more ductile. If you use the helical ties, the failure will be ductile. That is, the failure may not be sudden. It will yield compared to the column with lateral ties. So this is the column with the lateral ties. The failure, how the axial strain with respect to the load will vary. If in case of helical reinforcement, there will be some yield. The failure will be more ductile. This graph specifies that lateral tiles have less ductile failure when compared to helical reinforcement. The ratio of volume of helical reinforcement to the volume of core shall not be less than 0.36 Ag by C minus 1. Ag is the gross area of section, AC is the concrete area minus 1, FCK by Y. FCK is the characteristic strength of concrete, Fy is the characteristic compressive strength of reinforcing steel. Reinforcing steel here is the helical reinforcement. This value should not exceed Fe 415, that is 415 Newton per mm square. So this is all about the reinforcement, helical reinforcement for compression. Now let's learn about facts on interaction diagram. This is a typical interaction diagram between Pu and Mu. Pu is the design load, Mu is the ultimate moment of resistance. This point, the point number 1, represents there is no eccentricity. That is, the load is purely the line of action of load purely coincides with the axis of the column. So there may be zero eccentricity. There will be zero eccentricity. So there will be zero moment. So Mu is 0. Only Pu is there. The point 1 represents pure axial load. That is, E is equal to 0. Then where will be the E minimum, whether 0.5 or 0.4 or 0.3 or 0.2 or 0.1 dash? The E minimum will be at 0.1 dash. That is this point. This point will be the E minimum point. And the fourth point, that is this point, is represents the balanced failure. There will be both compression and tension. The compression tension will be balanced at this point. And the fifth point, that is, there is no load, axial load, but there is only moment, means this is the maximum eccentricity. It is nothing but E is equal to infinity. Here we have seen that pure axial stress is acting, axial load is acting. Then what will be here? It will be pure bending. So the balanced failure, below the failure envelope, below which there will be tension failure, above which there will be compression failure. So E less than E balanced will be compression failure. It will induce the compression failure. When eccentricity is getting more, then it will induce the tension failure or flexure failure. So this is all about the interaction diagram. The resistance of member subjected to axial force and biaxial bending shall be obtained by the satisfying following equation. So this equation is provided in IS 456. Mux is divided by mux1 power alpha 1, muy divided by muy1 power alpha 1 shall be less than 1.0. This is interaction equation is given in IS 456 code. So alpha n value shall be as follows. It is related to Pu by Puz, and Puz is nothing but 0.45 FCK ASC plus 0.75 Fy ASC. Right, this graph represents that if Pu by Pz ratio is less than or equal to 0.2, then alpha will be 0.1. Then Pu by Puz ratio will be greater than or equal to 0.8, then the value of alpha will be 2. Slender compression member, that is long column. Long column means what? The ratio will be greater than 12. L by D ratio will be greater than 12. An additional moment is considered while designing a long column, which is calculated as follows. This is the additional moment we have to consider for long column, long slender compression member, MAX and MAY. PUD by 2000 into LEX by D square. For y direction, PUB divided by 2000 LUY by B whole square. Design of long column is done as per procedure class number 13.5 and 13.6 of IS 456. So now let's move on to limit state of collapse. The nominal shear stress in beams of uniform depth shall be obtained by tau V is equal to VU by BD. Tau V is the nominal shear stress, VU is the shear force, B is the breadth, D is the effective depth. So nominal shear stress can be obtained by this formula. In case of beams of varying depth, this formula is used by the uniform depth beams. In case of beams of varying depth like this, the equation shall be modified as VU plus or minus MU by D tan beta divided by BD. So for this figure, the value will be minus. For this figure, the value will be plus. Obviously, tan beta, it is increasing gradient. So the tan beta will be a positive value, so plus. It is a decreasing gradient, so tan beta will be of negative value, so minus. Minus will come here. Vu plus or minus MU by D tan beta divided by BD. This is in case of beams of varying depth. Now, design shear strength of concrete. Design shear strength of concrete in beams without shear reinforcement is given in table 19 of IS 456. So, for solid slabs, the design shear strength of concrete shall be tau z k, where k has the values given below. Actually, this design shear strength is nothing but 0.63 root FCK. If you calculate 0.63 times root FCK, the design shear strength will arrive. For example, if we are using M20 grade of concrete, 0.63 into root FCK gives some design value of 2.8 shear strength value. So 0.63 root FCK is the design shear strength of concrete. In this table can be used for identifying the K value, overall depth of slab. If it is 300 or more, then K value will be 1. So likewise, shear strength of members under axial compression. For members subjected to axial compression PU, the design shear strength of concrete given in table 19 shall be multiplying by the following factor. Suppose there is an axial compression, member subjected to axial compression. That design shear strength value will be multiplied by this factor. The factor will be 1 plus 3 Pu by Ag FCK. Axial compression, for example, columns or pedestals, even though. Now, with shear reinforcement, under no circumstances, even with shear reinforcement, shall the nominal shear stress in beam tau v shall exceed tau c max given in table 20. So under no circumstances the shear reinforcement shall the nominal stress in beam exceed this value given in table 20, the maximum value. Minimum shear reinforcement has to be provided as per class 26.5.1.6 that we have already seen in reinforcement slide. That is ASV divided by B, SVS shall be greater than or equal to 0.4 by SV. Greater than 5. Now design of shear reinforcement. When we will design the shear reinforcement when there exists tau is greater than tau c. Forms of shear reinforcement are vertical stirrups, bent up bars along with stirrups, and inclined stirrups. These are some forms of shear reinforcement that we can provide. Where bent up bars are provided, their contribution towards shear resistance shall not be more than half that of total reinforcement. Shear reinforcement shall be provided to carry a shear equal to Vu minus tau z Bd. So shear reinforcement shall be provided to carry a shear. That value should be equal to Vu minus tau z Bd. And for various forms of shear reinforcement, there is corresponding formula. For vertical stirrups, it is about VUS is about 0.87 FYSVD by SV. For inclined stirrups, we shall multiply sin alpha plus cos alpha. And for single bar or single group of parallel bars, it is about 0.87 FYSV sin alpha. All bent up at the same cross section. And again, Fy value shall not be greater than F415. That is, we can use mild steel. Limit state of collapse. We have seen shear, flexure, and compression, and we are now going to see about the limit state of collapse, torsion. For torsion, critical section has to be located less than a distance d from the face of support that may be designed for the same torsion as computed at a distance d, where d is the effective depth. For torsion, we have to calculate the equivalent shear and equivalent moment. Equivalent shear will be calculated by using this formula. V is equal to Vu plus 1.6 Tu by B. Tu is the torsional moment, B is the breadth of member, Vu is the shear force. Equivalent moment shall be calculated by using this formula, Mu plus Mt. Mt is given by Tu into 1 plus overall depth divided by B divided by 1.7. If suppose Mt is greater than ultimate moment resistance, longitudinal reinforcement shall be provided on the flexural compression phase such that the beam can also withstand an equivalent Me2, which is given by Mt minus Mu. If suppose this value is greater than Mu, then again equivalent moment has to be provided, which is equal to Mt minus Mu. Now, this is all about the section 5 structural design limit state method. First, we have seen the limit state of collapse flexure, then we have moved on to compression, then we have seen shear, and at the last, we have seen the torsion. And now it's time to move on to the annexures. First, we shall see the Annex B, which is nothing but structural design working stress method. So far we have learned about the limit state method and limit state design. Now the IS codes also specify some criteria for working stress method, which uses factor of safety instead of partial safety factors, as like in limit state method. Now first, assumptions and other criteria. Since working stress method is based on elastic theory, working stress based on elastic theory, the following assumptions are made. Plane section remains plane before and after bending. This is already we have seen in limit state method also. All tension stress are taken up by reinforcement only. This is also we have seen in limit state method. The tensile stress shall be calculated as F by AS plus MAST, where M is the modular ratio. Stress strain relationship of steel and concrete is linear, unlike in limit state method, which is somewhat parabolic. Here it is considered as linear, that is straight line. The modular ratio M has a value of 280 by 3 sigma CBC. Sigma CBC is the concrete bearing 280 divided by 3 sigma compressive stress due to bending in concrete. M is equal to 280 by 3 into sigma CBC, where sigma CBC is permissible compressive stress due to bending in concrete. Actually, this value shall be in Newton per mm square. Where stresses due to wind, temperature, shrinkage effects are combined with those due to dead load, live load, or imposed load, impact load, the stresses in table 21, 22, 23 of IS 456 may be extended up to a limit of 33.33. That is 33 1 by 3 percentage. We can extend those values or increase those values by 33 1 by 3 percentage. Wind and seismic forces need not be considered as acting simultaneously, as we have already seen. Wind load and earthquake load should not be or need not be considered as acting simultaneously. Permissible loads in compression members. These are some provisions according to Annexure B of IS 456 to pedestals and short columns in lateral ties is given by this formula. As like in limit state method, it is about P is equal to sigma Cc AC plus sigma Sc AC. Sigma Cc is the permissible stress in concrete in direct compression. Sigma Sc is the permissible compressive stress for column bars. ASC is the cross-sectional area of longitudinal steel. Short columns with helical reinforcement. Again, we have to increase those load by permissible load by 1.05 times, and the long column has the coefficient. The maximum permissible stress in a reinforced concrete column having a ratio of effective column length to least lateral dimension about 12 is the long column, and shall not exceed that which results from the multiplication of the appropriate maximum permissible stress as specified by the coefficient CR. This is the coefficient we have to multiply with the maximum permissible stress, 1.25 minus L effective divided by 48B. And for more exact calculations, we can use the radius of gyration as a factor. Instead of B, we can use the radius of gyration. CR is equal to 1.25 minus L effective divided by 160 least radius of gyrations. So for composite columns, the cross-sectional area of the metal core shall not exceed 20% of gross area of column. This is most important line for composite columns. The cross-sectional area of the metal core shall not exceed 20% of gross area of the column. Other parameters such as shear, torsion, combined axial and bending, some other subject as we have seen in limit state method are very similar in case of working stress method also, but with minor changes. For example, we don't use partial safety factors in working stress method, we use only factor of safety. And the question for you is, to what extent the value of modular ratio make allowance for the creep of concrete? Modular ratio means what? 280 by 3 sigma CBC, or we can simply say that yes, that is the modulus of elasticity of steel divided by that of concrete. So modulus of elasticity, so modular ratio as given by working stress method is 280 divided by 3 sigma CBC, where sigma CBC is the permissible bending stress in concrete. So to what extent the value of modular ratio make allowance, whether it is full compression or full tension or partially compression or any other? So the answer will be partial compression only. For some amount of compression, the modular ratio will make the allowance for creep of concrete, but not for full compression. This is all about the annexure B. And next we move on to annexure D. Specifies the slabs spanning in two directions. For restrained slabs, when the corners of a slab are prevented from lifting, the slab may be designed as this the 1.1 to 1.11. So this is the formula for maximum bending moments per unit width. Per unit width means the bending moment will be coming under kilonewton per meter cube per meter. So per unit width, alpha x w l x. The alpha x alpha value will be given in, these are coefficients will be given in table 26. W is the total design load per unit area, Lx and L are the length of shortest and longest span respectively. For span Lx, this is the middle strip. This diagram represents the what is the edge strip, what is the middle strip, what is the edge strip. So Ly by 8, 1 by 8 of the Ly from the edge is the edge strip. 3 by 4 Ly at the middle is the middle strip, width of the middle strip, and this is the edge. For span Ly, this is the criteria: Lx by 8, 1 by 8 of the length of that axis, length in that axis. Slabs are considered as divided in each direction into middle strips and edge strips as shown in this figure. The middle strip being 3/4 of the width, 3/4, 3 by 4 of the width, and each edge of strip is 1 by 8 of the width. The tension reinforcement provided at mid-span in the middle strip shall extend in lower part of slab up to 0.25 L from center of support of its continuous edge or 0.15 L of a discontinuous edge. These are some criteria for slabs spanning in two directions. Similarly, for continuous edge, this is at a distance of 0.15 L from support, 0.3 L. It can be extended for at least 50%. For discontinuous edge, negative moments may arise. So, depending on which degree of fixity of edge of slab can be, in general, tension reinforcement equal to 50% of that will be provided at mid-span, extending 0.1 times L into the span. That will be sufficient. We will move on to the annexure E, which gives the effective length of columns. From table 28, we can see the effective length of compression members. For example, if we want to see the effectively held in position and at both the ends restrained against rotation at one end only. So your recommended value of effective length is the 0.8 L. Theoretical value as per sectional analysis is 0.70 L, which is nothing but L by root 2 actually. L by root 2 is the 0.707 L. But recommended value as from IS 456 is 0.80 L. We can use any of those things. For every end conditions, there is given a effective length for compression members. So this is all about the annexures part, and the last annexure, which gives the design for T sections moment of resistance, annexure Z. It is a very easier one, which is very similar to rectangular moment of resistances. For example, mu limit is nothing but 0.87 FIST D into 1 minus 0.416 XU, like this. T beam has to be designed on the basis of XU values, where it is located, whether it is in flange portion itself or whether it is located in web portion. Based on those things, we have to design T sections as per annexure G. So this is all about the summary of IS 456-2000. First, we have seen the section 1 as a general part. Then in general, we have covered the description of symbols. Section 2, materials, cement, aggregates, and inspection and testing. Section 3 is the general design consideration. Section 4 is the special design requirements for structural members and systems. Section 5 is the limited method of structural design, and some annexures we have seen, annexure B, D, E and G. So this is all about this video. Hope that this video is helpful to you. If you have any doubt, you can contact me at any time and you can post your queries in comments.